Hello and welcome to this lecture. In this lecture, we are going to do a little bit of fun stuff with the circle, perimeter, area, and introduce the number pi formally in this class. All of us know these formulae from a long time. Perimeter is 2 pi r, area of a circle is pi r squared, the number pi is roughly 3.14, and of course you can go to larger and larger decimals. But how are all these things defined? How do you formally do it? It turns out integration plays an important role in that also. Okay, and in the process, we will also define something called an improper integral. So far, we have defined integrals only for bounded functions in a bounded interval, right? Function is bounded, interval is bounded, we know integration. But quite often, you may want an area when the function is not bounded, or when the interval is not bounded, or you may want an arc length in that case, when maybe length is not very interesting, but area can be a little bit interesting. So it turns out some of those areas can still be finite. Okay, even if the function is unbounded, if there's only a thin strip that goes up, maybe that area will not be very big. Okay, so it still can converge. It's like a sequence converging type of thing. So we have not seen that so far. We're going to see that as one of the important subtopics when we define pi and perimeter of a circle and all that. Okay, so let's get started. Okay. So this problem of a circle, like I said, it's fascinated people for centuries, and from a very long time ago, this pi has fascinated people, right? It's known that whatever the circle's radius may be, however big the circle may be, the ratio of the perimeter to the diameter is always a constant pi. Okay, so lots of ways in which you can visualize this. Is wonderful visualization. If you go all along the equator with a rope and tie it up, and then if you lift the rope everywhere by 1 meter, it turns out you would imagine that the length of the rope may increase tremendously, but it doesn't, right? It increases by a very small number because perimeter to diameter has a constant relationship. It's a fascinating property, and there's lots of history behind it. I don't want to go too much into the history, but I'll encourage you to look it up. The ancient Indian civilization also knew a lot of things about pi. The Madhava series in particular is very popular here. Okay. Anyway, let's come back to our course and then look at what we do here. Okay, so I'm going to take a unit semicircle. Okay, what is a unit semicircle? This is the unit semicircle. The radius is 1. It goes from -1 to 1, and the function f of x defined by this red line is defined by basically square root of 1 minus x squared. So how does this square root of 1 minus x squared come from? It's easy to see. Okay, so the circle basically has an equation. The unit circle, for instance, has an equation. Radius is 1, this is 1 minus 1. This equation is basically x squared plus y squared equals 1. As in, you take any point xy, its distance, this distance has to be 1. Okay, so that is square root of x squared plus y squared is equal to 1, which is the same as x squared plus y squared being equal to 1. So if you collect all the points which are at a distance 1 from the origin, you get the circle, and that is what is described by x squared plus y squared. So if you want to describe y alone, you will get y squared is 1 minus x squared, which is y is square root of 1 minus x squared. So that's on the positive side. On the negative side, you will get y equals minus the square root of 1 minus x squared, right? So this part, maybe I should do blue here. This blue part on top is y equals square root of 1 minus x squared, and maybe the red part at the bottom is y equals minus square root of 1 minus x squared. So I'm interested more in the blue part, or at least that's what I've described here in this here. Okay, now it is red here, but anyway, it's the top part. So it is plus square root of 1 minus x squared, and that's the top semicircle. Okay. How does pi come about? So here is the important fact. We can now figure out the perimeter of the semicircle, right? What is the distance that I would travel if I go along this arc, this circular arc from -1 to +1. Okay, so that we know a formula for, no? It's integral -1 to 1, right? X equals -1 to x equals 1, square root of 1 plus this f of x, but I have to differentiate it, right? Square root of 1 minus x squared, I need to differentiate 1 plus f prime of x squared. Now this one, let me show you the simplification, ends up being equal to this number. Okay, so let me show you the simplification. F of x is square root of 1 minus x squared. What is f prime of x? It's 1 by 2 root 1 minus x squared, right? The composition rule, no? You think of 1 minus x squared as entirely one function you differentiate, and then you have to differentiate 1 minus x squared. That will be minus 2x. Okay, 1 minus x squared, if you differentiate, you get minus 2x. So 2 and 2 will cancel, you get minus x by square root of 1 minus x squared. Okay. Okay, you can do this by hand or you can do it on SymPy. SymPy can also do differentiation. Define this function, it will give you this answer. Okay, so you will get this f prime. Now, what is perimeter? Perimeter is minus 1 to 1 square root of 1 plus f prime of x squared. So, which is minus x by root of 1 minus x squared whole squared dx, right. So, when you square it, you are going to get what? This is going to become x squared by 1 minus x squared. Okay, and then you do a 1 plus, which will become 1 by 1 minus x squared, and then of course there is a square root, you retain that. Okay, so this becomes integral minus 1 to 1 by square root of 1 minus x squared dx. Okay, now this is a little bit of a complicated integral. It's actually become an improper integral. Why has it become an improper integral? If you put x equals minus 1 here, this function goes off to infinity, right? Right? If you put x equals minus 1, but I am coming from this side, like, from minus 1, even x equals 1, it goes off to infinity. Okay. So, there is a little bit of a problem here we have not seen. So, this is not a bounded function, but I am still writing an integral. So, what does that mean? Okay, I have to define that for you. I will postpone that to the next slide, but for now you assume that this is well defined. Okay, hopefully I will convince you in the next slide how we define this, but even though this is not bounded, this can be defined in a reasonable way, and we will do that in the next slide. But for now, stay with me because this is an important idea here. So, I have this integral minus 1 to 1 by square root of 1 minus x squared dx. So, how do I compute this? I do not know how to find a closed form for this, but I can do my SciPy NumPy definition. Okay. So, look at this. What I have done here is I have imported SciPy, just now I showed you, imported NumPy, and then I have integrated with the quad function, defining the function 1 by square root of 1 minus x squared minus 1 1. Okay. And here is the little piece of magic. All of you might know this already. You will get pi. Okay, this integral will give you pi. Okay, you all know that the perimeter of a semicircle is pi, unit semicircle, right? It's pi r, and r is 1, so it's pi, and no wonder that this integral will be equal to pi. So even if you did not know what pi was, I am going to formally define for you the perimeter of the unit semicircle to be pi. Okay, and that is defined as this integral minus 1 to 1 by square root of 1 minus x squared. Notice this is an even function, no? You remember our definition of even function? This function, if you put instead of x, if you put minus x, you get the same thing. Okay, so this is an even function. So this integral will simply become 2 times integral 0 to 1 by square root of 1 minus x squared dx. This is my definition of pi. This is the value of pi. This is the perimeter of the unit semicircle. So what is the perimeter of the unit circle? It's 2 times pi. Okay, and this pi has this value 3.1415 whatever by this integration formula. But before we go further, I have to tell you how this integral is defined, right? It seems to be an improper integral. This is not a bounded function. How does that work? So let's settle that first, and then we'll come back and look more closely at perimeter of a arbitrary circle and area and all that. Okay. So what is an improper integral? This improper integral of pi had this function 1 by root of 1 minus x squared. So here is where I have plotted 1 by root of 1 minus x squared. So you can see these numbers is 1, 2, 3, etc. and from minus 1 to 1 for x, right? At 1 it is, at 0 it is 1, that's okay. But as you get close to 1, this function goes unbounded and very, very large. Okay, and here as it goes to minus 1, it's growing unbounded and very, very large. But hopefully you see that the area here is very tiny, It's really a tiny small area. The most of the area, bulk of the area is here, and that is very small. Maybe that area will converge, right? That's going very, very increasing so slowly that maybe it will converge. Okay, so that kind of convergent definitions for an unbounded integral is called an improper integral. This is actually not bounded, but we can define it as the limit of a series of bounded integrals, and that you get an improper integral. So we have seen this before, right? When you have a limit of a sequence of things and that converges to something, we usually call that as a convergent value. We call it a real number, and that's very, very useful. Same thing we do here. This integral will in the limit converge, and we'll call that limit as the pi value. Okay, so that's interesting. So improper integrals are limits of proper integrals, and this is how we define it. Okay, so if you look at this integral from minus 1 to 0. Okay, minus 1 to 0 I will define. I will define it as, so forget about this limit for now, just look at this integral. Integral s to 0 1 by root 1 minus x squared, and I will take s to be something other than minus 1, something greater than minus 1, say minus 0.9, minus 0.95, minus 0.995, minus 0.999995. Okay, any value other than minus 1 I take for s. I have a proper definition for this integral. Yes, I do. Yeah, I can define this integral properly for any value of s that is not minus 1, right? Integral s to 0. That will work as close to minus 1 as possible. That is what I mean by taking to the limit. So, in the limit as s tending to minus 1 plus, if this limit exists after this integration, then we define that as the improper integral. I will simply, instead of writing this limit, I will simply write minus 1 here. But you have to know that there is a limiting operation here, and that people quite often get into trouble if they forget that there is a limiting operation. But in general, we will simply write it as minus 1. Okay. What about minus 1 to plus 1? This is very important here. There are 2 points where it is diverging, right? So, you have to split it into 2 integrals. Okay. The first integral is s to 0, limit as s tending to minus 1 plus. What is this minus 1 plus? I am approaching minus 1 from the positive side, right, from the right side, that is minus 1 plus. Likewise, this other integral, integral 0 to t 1 by root 1 minus t x squared, this will exist for any t less than 1. So, if I approach 1 minus, right, t tending to 1 minus from the left side, if I approach 1, this integral will exist, and if this limit exists, then I can define this integral as the improper integral. Okay. So, this notation, even though there is no limiting mentioned here, is actually a limiting operation, not just one limit, there are 2 limits, one on this side, one on that side. Okay. So, you have to be very, very cautious with improper integrals for this reason. Okay. If you forget that there is a limit here and happily do whatever, you will end up with big trouble. Okay. So, you have to remember that there is a limit here, and as long as you remember that, you will be okay. Okay. But generally it will work, okay, but you have to be careful. In some cases you can get into trouble if you forget that there is limiting. Okay. So, integral minus 1 to 1, 1 by root 1 minus x squared dx is well defined if these 2 limits exist. It turns out these 2 limits exist, and I am not going to prove it here, but it is possible to show that these 2 limits exist. So, this improper integral exists. So, pi exists as some proper number. So, we did it numerically and confirmed that it is okay, but you can also prove it using some other methods. Anyway, the perimeter is a finite length, right? I mean, it cannot not exist. So, physically it is okay to believe in this. So, this is how improper integrals work. Okay. I hope this is clear to you. We can, so before we proceed, let us see a few examples of an improper integral, just to warn you that what works, what does not work. Here is an example, integral 0 to 2 1 by root x. Okay. First thing, you have to convince yourself that this is an improper integral. Why? Because at 0 this is going unbounded. Okay. We do not have a way of doing proper Riemann sum definitions when functions go unbounded, right. So, it will go off to infinity, it does not work. Okay. So, we cannot do it correctly. What we will do here is, we will instead put, instead of 0 here, we will put a s, okay, and then tend s to 0 in the limit. Okay. So, this is our actual definition of this guy. Okay. When you write like this is the definition. Okay. There should be a limit here, except we swallow it. I will tell you why the reason we swallow it is. Okay. Here is limit as s tending to 0. What is 1 by root x? The integrand is 2 root x, right? The antiderivative of 1 by root x is 2 root x. So, use the fundamental theorem of calculus, you get 2 root x evaluated between s and 2. Now, when you do between s and 2, it just comes out as 2 root 2 minus 2 root s. Okay. So, if you take the limit as s tending to 0, this will go away, you will get 2 root 2. Okay. So, a lot of people, when they do improper integral, will happily forget this limiting operation. You do not need this limiting operation, right. Forget that the limiting operation exists. You simply do integration as it is. You just do 2 root x, right. Substitute between 0 and 2, you get the answer, no. So, that is why this limit is often forgotten in improper integral, but it is not the correct thing to do. You should remember that there is a limit. The reason is, see, the integration itself is a limit, you know, there is a limit, there is one more limit here, okay, and these kind of successive limits are a bit difficult to deal with. Okay. So, there is some theory around it, we will skip that, it is a bit technical. So, this limiting is an important thing technically, but mostly when it works, it will work very, very smoothly. You can forget about the limit, right. You can simply forget about the limit, just erase this part, right. 1 by root x, I know 2 root x is the antiderivative, I substitute between 0 and 2, do not even write limits, 0 and 2, you will get 2 root 2 minus 0, 2 root 2, answer is correct, right. So, unbounded functions, you can do improper integral in this fashion. You may also have an unbounded limit of integration. So, how does that work? So, you can do an integral from 1 to infinity of 1 by x squared dx, okay. So you can imagine the 1 by x squared, right? From 1 to infinity, 1 by x squared is falling. So maybe the area is very small, maybe the area will be something finite, right? So how do you actually define this? This should be a limit as t tending to infinity, integral 1 to t 1 by x squared. This is the proper way to define it, okay? And this will be again, now once you have 1 to t, any finite t, I know that this is a proper integral, this works. So I do minus 1 by x between 1 and t, that is minus 1 by t plus 1, and 10t to infinity, you get 1, okay. Here also I want to remind you, you can forget about this limiting operation and go directly from here to here, okay, and then simply put infinity here, right, because 1 by x square is minus 1 by x, and you evaluate it between 1 and infinity, you get this answer, okay. So it works out very smoothly in most cases, but in cases where it doesn't work out, you can get into trouble if you blindly do this, okay. Here are a couple of examples where it doesn't work, okay. So here is an example. If you do integral 0 to 1, 1 by x, it won't work. We don't know what the antiderivative of 1 by x is. It turns out it's log x, and if you do log x substituting 0 will go to minus infinity. So it doesn't work. So we'll see logarithms a little later in this set of lectures, but it turns out this is not a proper, I mean this, even the improper definition doesn't work here. So again, another example is integral 1 to infinity 1 by root x. 1 by root x is not falling as fast as 1 by x squared. So if you do the antiderivative, you will get 2 root x, and if you put infinity, it goes up to infinity, okay. So it can blow up, these things can blow up, and you may not get convergence, but in some cases, in many cases it will work, and in the pi case also it works, okay. Okay, so let's now come back to the perimeter of circle of radius r. So in the problems, we'll look at some improper integral and get you some practice with how to deal with improper integration. But before that, let me complete the story of the circle. It's a fascinating story. Let's look at the semicircle of radius r. Okay, now instead of unit circle, I've gone to radius r. For r, what is the formula? X squared plus y squared equals r squared, right? That's the formula for the circle, and f of x is basically square root of r square minus x square. And I am going to integrate from minus r to r, okay. So what happens now, if you look at the perimeter of the semicircle, and if you do square root of 1 plus f prime of x squared dx, you will get this guy, okay. So this is the easy thing to do. If you do f prime of x, it is 1 by 2 root r squared minus x squared times minus 2x, so it will be minus x by square root of r squared minus x squared. If you square it, you will get x squared by r squared minus x squared, multiply and add with 1, you will get r squared by r by root of r square minus x square. So this is an easy enough definition to make. So here is the little trick here. So where does pi come from? It doesn't look like pi is coming from. What is pi? Pi is integral minus 1 to 1 by root of 1 minus x square, right? This r seems to be showing up here, and the trick here is to make this substitution, u equals x by r, okay. This is an important little substitution. You can see why that is done. I want to convert my radius r into the unit circle type thing, okay. So when you do that, you will get this change. So let me just show you how that change happens, maybe real quick here. So integral minus 1 to 1 minus r to r by root of r square minus x square dx, and I want to make the substitution u equals x by r, okay, sort of divide by r to get 1. So you remember this du conversion, right? Du is dx by r, so dx is r du, okay. And then x, I am going to put u minus r. So this is x equals r. So this is u equals x by r. So it's minus 1 to 1. Okay. So I have r as it is. The square root of r squared minus x is u square r square. Dx is r times du. Okay. Is that okay? So you have r squared here, and the r squared will come out here, and it will cancel with that r, and you will simply get r times integral minus 1 to 1 by root 1 minus u squared du. Okay, and what is this? What is this? This is pi. Okay, so you get this fantastic little formula, which after you substitute u equals x by r, that this integral, the perimeter of the semicircle, simply becomes pi times r. So if you go a radius r away, right, the unit circle has unit semicircle has perimeter pi. If you increase the radius to r, you have to simply multiply pi with r. Okay, the perimeter simply scales with the radius in a linear fashion. The constant is pi. Okay, so that's a beautiful, beautiful result, and this is a very, very famous formula. Perimeter of a radius r circle is 2 pi r. It's pi r for the top part, pi r for the bottom part. You get 2 pi r, and this gives you this wonderful, wonderful fact that pi is indeed the ratio of perimeter diameter of any circle that you can draw of any radius. Okay. So, this sort of completes the picture of perimeter of the circle of radius r, and you can see the central role integration plays in this. Okay. So, let us move on to the area of a circle. Okay. So, once again I will start with a quarter unit circle, just the quarter now, not even the semi. Okay. So, we are just doing a quarter from 0 to 1. The function is still root of 1 minus x squared, x is going to go from 0 to 1. Okay. So, this is a quarter of a circle. It is enough if I find this area, right. The area of the circle is 4 times this. So, it is enough if I find this area, and I am starting with the unit circle. You can again do the trick when you go from unit circle to arbitrary radius r and do the substitution u equals x by r, you will get the same value, similar type of answer. So, let us do this problem first. Okay. This is a classic area under the curve problem, right. This is area now, not perimeter. So, you have root of 1 minus x square as this curve, and I need to find the area under it. Okay. So, the area of the quarter unit circle, I will call it A. It is simply integral 0 to 1 root of 1 minus x squared dx. Okay. At the outset, this seems very different from the integral 1 by root 1 minus x square, right. I know that the area is connected to pi from my prior knowledge, I know that. So, somewhere pi has to enter the picture, but pi does not seem to be here, no, it is just area is integral 0 to 1 square root of 1 minus x square. Where am I going to get 1 by square root of 1 minus x square from, right. So, here again you can use our wonderful little substitution trick, okay, and you will see magically things will work out. Okay. So, I am going to substitute u equals square root of 1 minus x square. Okay. And you can do the work here, you can do du, which will be minus x by root of 1 minus x squared, du dx, and then x will be square root of 1 minus u squared, what you have below will be u. So, you have a du dx conversion. Okay. Now, you plug that back in there, you are going to get this a to be also equal to integral 0 to 1 u squared by root of 1 minus u squared du. Okay, notice how this simple substitution, suddenly this root of 1 minus u square has come, right. Now almost there is a pi, right. Integral 0 to 1 du by root of 1 minus u square is like pi by 2 or something, right. But then I have this u square disturbing me there, right. I do not want this u square, except for this u square I seem to be home. What do? Here is another trick. You write u square as 1 minus u square. Okay. So, this is the same as u square, I have not done anything else. So, notice all these small little adjustments and tricks that give you fabulous answers. Okay. So, you have this u square is 1 minus u squared, and then now I am a little bit closer, right. So, now I will split this this fraction into 1 by root of 1 minus u square and minus 1 minus u square by root of 1 minus u square. What will that become? Root of 1 minus u square again. Okay. Notice from this I have come to this, and both these are the same. Okay. Now, you can identify some things very nicely. This guy, this integral I know is pi by 2, right, and this integral I know is a again. So, a equals pi by 2 minus a, which gives me a equals integral 0 to 1 square root of 1 minus x square dx, and that is pi by 4. Okay. Hopefully, you saw how this u and x, the dummy variables, do not matter, right. I hope you see that it is the exact same thing. Okay, you have to pay attention to this. I mean, there is a minus sign. What happened to the minus sign? Where did the minus sign disappear? So, notice if I do minus, when I do u equals root of 1 minus x square, if I put x equals 0, I will get 1, and if I put x equals 1, I will get 0. So, this integral limit will become 1 to 0, and that will absorb the minus and become 0 to 1. Okay, so that also is happening here. So, okay, do this change of variables and convince yourself that that's true. Okay. So, here by this small little manipulation, we have another formula for pi. Pi is not only 2 times integral 0 to 1 by root 1 minus x squared, pi is also 4 times integral 0 to 1 root of 1 minus x squared dx. Now, this is a proper integral, isn't it? There is nothing improper about it, right? It's pakka and proper. So, this is a way to convert an improper integral into a proper integral and then relate it to pi once again. Okay, so pi has another integral formula which is proper itself. There is no improper here. Pi is just 4 times integral 0 to 1 root of 1 minus x squared dx. Okay, in particular, this gives us this beautiful formula that area of the unit circle, which is 4 times a, is just pi. Okay, and if you do the same adjustment, you will get the area of the radius r circle to be pi r squared. Okay, so these are very famous formulae that you always knew, and this is one way to sort of rigorously show them and how this pi shows up in this wonderful way as far as the circle is concerned. As from your experience, you would know that the pi shows up everywhere. Pi is such a useful and universally useful quantity and its central reason is that it controls, it arises in the circle in a very natural way, and both in the area and in the perimeter, and both of them are related. Okay. So this is also, I hope you are convinced that this is also proof that that improper integral is finite, right? This is a way to prove it. You can do the substitution and you will get to the answer. Okay. Okay, so let's go to some problems. These problems are to get you practice with improper integrals. Okay, so here is integral 0 to infinity e power minus x, right? So e power minus x is very nice. You know it's minus e power minus x is the integral, and you can substitute between 0 and infinity, right? If you put infinity, you're going to get 0, 0 will get 1. So basically, this integral will become 1. Okay, so let me maybe show that to you once. Okay. Integral 0 to infinity e power minus x dx. Okay, this will just be minus e power minus x between 0 and infinity. Notice how I am forgetting about the limit and all that. It's very easy to do. So e power minus infinity will go off to 0, and e power 0 will go to 1. So it is 0 minus of minus 1. So that is just 1. Okay, so you see that this integral is there, and the other two integrals are also similar. I am going to skip it. You can just find the integrand and then substitute 0 infinity, you will get the answer. Okay, so let me take this fourth problem, which is integral minus 1 to 1 by cube root of x squared. So in this case, when you have this kind of integration, one needs to be a little bit more careful. It's cube root of x squared dx. Okay, but notice why is this an improper integral, right? So the function is unbounded at 0. Okay, this is going to infinity at x equals 0. So this is the problem. So this is why this is an improper integral. So somewhere in the middle it goes unbounded. So for that, what you have to do, there is two things you have to do very carefully. So you split the integral into 2. Okay, you go around the point where it blows up. Okay, and then each of these things have to converge. This has to converge. Both integrals have to converge. And only then you can say that the improper integral will work out. Okay. So for this, I need to do x power minus 2 by 3. If you do antiderivative for x power minus 2 by 3, right? So that will be x power minus 2 by 3 plus 1 by minus 2 by 3 plus 1. So that will become 3 times x power 3 times x power minus 2 by 3. Okay. Or you can write, 3 times x power 1 by 3. Okay, I hope I got this right. Yeah, 3 times x power 1 by 3. Okay, so you have 3 times x power 1 by 3, and so that I have to evaluate between 0 and between minus 1 and 0. Okay. And then you also have the same 3 times x power 1 by 3 evaluated between 0 and 1. So here you will have 0 minus of minus 3. Okay. So minus 1 cube root, I have to take it as minus 1, right? That is the cube root, plus 3 times, that is 3 minus 0, and so you will get 3 plus 3 being 6. Okay. So there's numerous other things you can do, but you have to pay attention to why the integral is becoming improper, where it is going unbounded, split the integral into 2. In most cases it may work quite easily, but pay attention to that, you will get the correct answer. Okay, so the last one I am going to skip. It's just a routine integral, the limit going off to infinity, and this is 1 by x plus 5 power 5. You can find the antiderivative easily. Okay, so that sort of sums up improper integrals, which is an important trick that you learned here, and also circle. Okay, where does pi come from? What is the integral definition for pi? And how do you find area of a circle, perimeter of a circle? What is the properties of pi, etc. Okay, thank you.